Ever stop and think about the invisible language that's running literally everything you own? You know, your phone, your laptop, it all operates on a set of rules called digital logic. Well, today, we're going to pull back the curtain on a really cool concept: how the same exact digital instruction can be written in two completely different ways. One is like a super detailed blueprint, and the other, it's a clever shortcut. Let's dive in.
So here's the big question, the puzzle we're going to solve. How on earth can two logical statements that look totally different from each other actually mean the exact same thing? I know, it sounds kind of impossible, right? But it's the secret sauce to making all of our electronics fast and efficient. Stick with me and we'll figure this out.
All right, to get our heads around this, we first need to understand that there are two basic ways to describe any logical outcome. Just think of them as two different languages telling the same story, but from completely opposite points of view. So on one side, you've got sum of products, or SOP for short. This language only cares about the times when the output is true, or a 1. It's basically asking, when is the light on? Then on the other side, we have product of sums, or POS. And yeah, you guessed it, it does the exact opposite. It focuses on all the times the output is false, or 0. It's asking, when is the light off? See? Both are describing the very same light switch just by looking at its different states. Okay, now it gets even more interesting. Within each of these two languages, there are two different styles you can write in. One that's incredibly detailed, the unabridged version, if you will, and another that's simplified and way more practical. This is what I call the blueprint versus the shortcut. First up, let's talk about the canonical form. This thing is the master blueprint. Seriously, it is the most complete, exhaustive description of a logic function you can possibly write. And it has one golden rule. Every single term in the expression has to contain every single variable involved in the function. There is absolutely zero room for interpretation. And here's what that rule looks like in practice. Say we have a function with 3 variables, a, b, and c. Just look at that expression. Notice how every single one of those terms has a, b times and c in it? That's the blueprint, in its purest form. And because it's so specific, listing out every single on condition, there can only be one, and I mean only one, unique canonical expression for any function. But here's the catch. If you actually tried to build a circuit from that master blueprint, well, it would be huge and super inefficient. And that's where the standard form comes in to save the day. This is our optimized shortcut. It's what you get when you take that massive blueprint and use a bit of math to boil it down to just its most essential parts. This example shows the difference perfectly. We have f equals a prime b plus bc prime. See that? The first term, a prime b, is missing c, and the second term, bc prime, is missing a. But here's the kicker. It still represents the exact same logic as a much longer canonical form, just, way more concise. This is the version you'd actually want to build with. So let's just nail this down. The canonical form, our blueprint, is totally unique and comes right from the truth table, but it gives you big, clunky circuits. The standard form, our shortcut, is the sleek, simplified version. And while you could have a bunch of different-looking standard expressions for the same function, they all lead to smaller, faster, more efficient circuits. And in the world of chip design, trust me, efficiency is everything. Okay, so we've got these two different languages, SOP and POS. How in the world do we translate between them? Well, it turns out there's this really slick method that honestly feels kind of like a magic trick. We'll call it the Minterm Shortcut. The thinking behind this is actually really simple but so powerful. If our sum of products expression tells us all the ways to get a 1, well, then everything that's not on that list must be the ways to get a 0, right? So by finding those missing pieces, we can build the product of sums version. It's just 5 simple steps. All right, let's get our hands dirty and walk through a real example. We're going to take this sum of products expression for a function f, and we're going to flip it into its product of sums equivalent. So first things first, we list out all 8 possible minterms for our 3 variables, 0 through 7. Then we just play a game of matching. We look at our function and check off which minterms are actually in it. And as you can see, our function uses the ones for the decimal values 3, 4, and 7. These are all the conditions that make our function spit out a 1. Okay, so what's the next logical step? We figure out what's not on our list. These are our missing minterms. And in this case, that's the ones for the numbers 0, 1, 2, 5, and 6. And what do these represent? They represent every single combination of inputs that makes our function output a 0. Now for the cool part, the magic trick. For every single one of those missing minterms, we're going to create its opposite, which is called a maxterm. And the rule is so easy. Just flip every variable. A prime becomes A, B becomes B prime, C becomes C prime. You get the idea. This instantly converts the description of a 0 output from one language to the other.
And for the grand finale, we just bring all those new max terms we made and stick them together with AND operators. And voila, there you have it. This new expression, the one that describes when the function is off, is a perfect logical twin to the one we started with. We've successfully translated from SOP to POS. So we've gone through the theory, we've seen the blueprint, the shortcut, and even how to translate between them. But why does any of this actually matter in the real world? Let's bring it all back to the physical hardware.
This is where it all clicks into place. That shortcut form we talked about, it's not just some academic exercise. It is the entire foundation of modern electronics. A simpler expression means a circuit with fewer physical parts. That means a chip that is physically smaller, cheaper to produce, uses less electricity, and runs faster. This one act of simplification, when you repeat it billions of times over on a single chip, is literally what makes the phone in your pocket possible.
So we've just cracked the code on one of the fundamental languages of our digital age, the logic that transforms massive blueprints into elegant, efficient shortcuts. And it really makes you wonder, doesn't it? What other secret languages, what other hidden systems are out there right now, silently and efficiently running the world all around us?